In this lab, I observed the motion of an object falling from rest and compared my observations to the predictions of two different models. The motion that I observed was that of a small knit doll that I dropped while standing on a stepladder. I calibrated the length scale and tracker using the length of the doll, and I chose my axes so that the position from which I dropped the doll was the origin, and the motion of the doll was along the y-axis in the negative direction. And then use tracker to obtain the position of the doll every 0.33 seconds, starting at the time t equals 0 seconds and ending at my last observed position at the time t equals 0.633 seconds. To model the motion of the doll, I used Newton's second law. For the first model, I assumed that the only significant force on the doll was the gravitational force of the Earth on the doll. This force has a magnitude equal to the mass of the doll times the gravitational constant g and is directed toward the Earth, which for my choice of coordinates is in the negative y direction. To implement this model, I used the following code. I found that the mass of the toy was 0.08 kilograms. I set the initial position to be the point from which I dropped the toy, which I found in tracker to be this position. Since I dropped the toy from rest, I set the initial velocity of the toy to be the 0 vector. Then, starting with the time t equals 0, I use Newton's second law with the net force of the gravitational force of the Earth on the toy to find the position of the toy over the same time period over which I had observations. When we run this, we see that the visualization of the motion is very similar to the observed motion of the toy. For my second model, I assumed that along with the Earth's gravitational force on the toy, there was also a drag force. To model the drag force, I assumed that its magnitude was proportional to the square of the magnitude of the velocity of the toy, and that it was directed in the opposite direction to that of the motion. For my choice of coordinates, that meant that the direction of the drag force was the positive y direction. In order to determine what constant of proportionality I would use, I tried different values and compared the resulting model's position at the final observation time to my observed position at that time. The value which led to the model matching most closely at that position was 0.010 kilograms per meter. To implement this model, all of my initial conditions remained the same, and I added an expression for the drag force, and my net force became the sum of the weight force and this drag force. My constant proportionality was 0.010. When we run this, we see that, again, the visualization of the motion is very similar to the observed motion of the dropped toy. Once I had all of the data from both models and my observed positions, I plotted the y-coordinate of the position predicted by each model and the y-coordinate of my observed position versus time on one graph. I found that the second model, which had a net force that consisted of both gravity and a drag force, resulted in a closer match to my observed position, particularly toward the end of the fall. In the first model, where the net force is the gravitational force of the Earth on the toy, if we look at the y-coordinate of the velocity vector, we see that over any time interval, delta t, there is a non-zero change, so there is no terminal velocity. However, in the second model, if we look at the y-coordinate of the velocity vector, then we see that if the magnitude of the velocity satisfies this equation, then over a time interval delta t, there will be no change to the velocity. So there will be a terminal velocity, and we can use this equation to find an expression for its magnitude, which is this, which for the particulars of my model lead to a terminal velocity of 8.85 meters per second. I confirmed this computationally using the code for my second model and allowing the object to fall for 4 seconds. I changed the code so that instead of plotting the y-coordinate of the position vector versus time, it plots the y-coordinate of the velocity vector versus time. The other coordinates of the velocity vector will be 0. It does appear that the velocity is approaching a limiting value and becoming nearly constant. At the end of its computation, I had it print out the final velocity vector, and we see that it has magnitude very close to that which I computed. If instead of being dropped from rest, the object was thrown down, say with an initial velocity of 0, -10, 0, then using the second model, the object will have the same terminal velocity. Here again, I plotted the y-coordinate of the velocity vector versus time, and it appears to approach the same limiting value. However, in this case, the magnitude of my initial velocity was larger than the magnitude of the terminal velocity, so the speed of the object is decreasing as it approaches the terminal velocity.